As climate change, population growth, and pollution continue to put pressure on freshwater supplies, the search for alternative sources of clean drinking water has become more urgent than ever. Around the world, millions of people face daily challenges accessing safe drinking water. In response, researchers and companies across different countries are turning to an unconventional but promising solution: extracting water directly from the air using solar-powered technology. This concept, known as atmospheric water generation, or AWG, is not new. The air around us contains varying amounts of water vapor, an often overlooked source of fresh water. With the right technology, this moisture can be captured, condensed, and purified to produce drinking water, even in remote or drought-stricken regions. What is new, however, is the pace of innovation. In just the past few years, multiple groups across the globe have developed and demonstrated advanced solar-powered devices capable of harvesting water from the air in more efficient, sustainable, and affordable ways. This video will explore the current landscape of solar water from air technology. We'll look at the major players and their innovations, how far along these systems are in development, the challenges they face, and what the future may hold for this life-changing technology. Across different continents, researchers and entrepreneurs are taking unique approaches to water from air devices. Here are some of the most notable developments to date. One of the most exciting breakthroughs comes from a collaboration between Australian and Chinese researchers who have developed a sponge-like material derived from wood. Infused with advanced properties and guided by artificial intelligence during its design, the material efficiently absorbs moisture from the air. Once exposed to sunlight, it releases clean water, no external power needed. Remarkably, this device can function even in cold and dry environments, expanding the potential use cases far beyond tropical regions. It is now in talks for pilot-scale production with industry partners, indicating that it's well on its way to real-world testing. Another Australian invention, the Hydro Harvester, has the capacity to generate up to 1,000 liters of water per day. Unlike traditional AWGs that rely on cooling air to its dew point, this system works by heating air instead. This approach is particularly effective in hot and arid environments, where conventional systems struggle. The Hydro Harvester can operate using solar energy or waste heat, making it an energy-efficient option for water-stressed regions. At King Abdullah University of Science and Technology, researchers have built a solar-powered AWG that automates the water harvesting cycle. The smart cycling solar device switches seamlessly between absorbing and releasing water using solar energy alone. It's capable of producing 2 to 3 liters per square meter per day. Built using low-cost and readily available materials, the device is designed to be scalable and affordable, making it especially appealing for deployment in large, off-grid areas with limited water access. The Massachusetts Institute of Technology, or MIT, has spent several years developing a solar-powered device that can extract drinkable water from dry air. Through continuous refinement, the system has seen improvements in efficiency and water output. The latest versions demonstrate that even in low-humidity environments, it is possible to capture enough water to meet basic daily needs, an encouraging sign for communities in semi-arid regions. Genesis Systems, a US-based company, has already brought a commercial product to market. Their device, called the Water Cube, is a compact, portable atmospheric water generator designed for residential, off-grid, or emergency use. Capable of producing over 10 gallons or about 38 liters of clean water per day, it's available now and represents a significant step toward consumer-ready AWG technology. The Water Cube is aimed at households, disaster relief teams, and remote communities needing a reliable, independent water source. Researchers at Northumbria University in the UK have developed a lightweight, solar-powered device that's intended for use in rural communities. Designed with portability and ease of use in mind, the system can be quickly deployed to provide clean drinking water using only sunlight and ambient air. Such solutions could prove especially useful in developing regions or areas affected by a humanitarian crisis. The journey from lab prototype to commercial product is well underway for many of these systems. Here's a closer look at how mature this technology is and where it's heading. Over the last decade, AWG systems have moved out of controlled lab environments and into real-world testing. Multiple prototypes have been successfully demonstrated under real environmental conditions, including in remote communities and harsh climates. Researchers have made impressive strides in materials science, using advanced hydrogels, hygroscopic salts, and even natural materials like wood to improve moisture absorption. Some systems are fully passive, requiring no electricity or moving parts, while others integrate sensors, AI, and automation to optimize performance. The most advanced example of a commercially available AWG is Genesis Systems' WaterCube. It's already on the market and being used in off-grid locations, emergency response operations, and sustainable housing projects. Other systems, like the Hydro Harvester and AI-guided wood sponge, are in advanced stages of development. Field trials are underway or being planned, with commercial availability expected in the next few years, depending on performance during testing and the success of partnerships with manufacturers. Meanwhile, universities and independent research centers continue to refine their systems. The goals are clear: increase efficiency, reduce costs, improve portability, and expand functionality to work in a broader range of environments. New innovations are continually being tested, including devices that operate at night, absorb fog, or are integrated into building materials. As promising as solar water from air technology is, it's important to understand its limitations. Not every environment is suitable for these systems, and several factors can affect performance. Most atmospheric water generators work best when the relative humidity is above 50%. Performance drops significantly in dry regions, especially when humidity falls below 35%. In deserts and arid zones, where clean water is often most needed, this presents a serious challenge. Only a few advanced systems using sorbent materials can function below these levels, and even then, water output is limited. Typically, warmer air holds more moisture, which means tropical and equatorial regions, where it's hot and humid, are ideal for water from air technologies. In colder climates, however, the process becomes more energy intensive because it requires cooling the air below its dew point to release moisture. Passive systems that rely entirely on environmental conditions are only effective in specific geographic regions where dew, fog, or high humidity levels are common. Active systems, those using sorbents or thermal cycling, can expand operational zones but may still struggle in areas with extremely low humidity or high altitude. In tough environments, more energy is needed to extract the same amount of water, reducing the overall efficiency and raising costs. While large-scale atmospheric water generation systems housed in factories or controlled environments can overcome these limitations, smaller portable units remain contained by local weather conditions and energy availability. For communities in suitable environments, such as warm, humid, and sunny regions, these solar-powered atmospheric water generators offer a valuable supplemental water source. They are particularly useful for off-grid living, emergency relief in disaster zones, remote rural areas, military operations, and sustainable housing. However, even the best systems may have days when they produce little or no water due to poor atmospheric conditions. Users need to understand that these devices are most effective when integrated as part of a broader water strategy, rather than as a complete replacement for traditional sources. In conclusion, the vision of pulling clean drinking water from thin air using only sunlight is no longer science fiction. Thanks to the work of researchers and companies across the globe, solar-powered atmospheric water generators are rapidly evolving. Some are already in commercial use, while others are entering pilot trials and preparing for mass production. In suitable environments, those with high humidity and abundant solar energy, these technologies can significantly improve access to clean water. For off-grid communities, disaster zones, or areas facing water stress, they offer a sustainable, decentralized water source. However, these systems are not a one-size-fits-all solution. Their performance depends heavily on local climate conditions, and in dry or cold regions, they may be impractical without added energy input or specialized equipment. Nonetheless, with continued research and investment, solar water from air devices have the potential to play a key role in addressing the global water crisis, especially as part of a diverse, adaptive approach to water management in a changing world. Before you go, check out some of my other videos. Don't forget to hit that like button and subscribe. Thanks for watching. We'll see you at the next one.